My name is Kathy Owen, and I'm currently the Deputy Branch Chief of the Structural Dynamics Test Branch, which is ET40. From nearly the beginning of the task, the IVGVT task, which was 2006 in that time frame, I have been the lead test engineer for the test laboratory here at Marshall. And the test laboratory was tasked with a lot of the responsibilities for the IVGVT, and that included the actually stacking the vehicle, preparing the facility, all the special test equipment design, the test conduct, and the development of the suspension system, as well as all the other test operations.
My name is Jerry Oakley. I'm a member of the Structural Dynamics Test Branch and Test Laboratory. Early in 2007, February of 2007, I became the foster parent of the 4 hydrodynamic suspension units, or HDSs, that were located in Building 4550, which is the large dynamics test stand. These units were delivered to Building 4619, and I was assigned the task of looking at these units and evaluating the possibility of using them for future ground vibration testing.
My name is Burleigh, and I'm a senior systems engineer here at NASA. My role in HDS refurbishment for Ares 1 was to take responsibility for the entire hydraulic support system. That pretty much includes all aspects with that system, from the design of the system to implementation, troubleshooting of the system, from the utilities all the way out to the HDS unit itself. I've worked a good bit with the controls engineer and where his system interfaces with the hydraulic system, and also with Jerry Oakley, who's the NASA lead on this, on the HDS unit itself, where the hydraulics feed into the HDS unit, and also where we gravity feed the oil off of the HDS unit. So, in a nutshell, everything associated hydraulically with the hydrodynamic support would be my responsibility.
The risk being addressed in this knowledge-based risk activity for IVGVT is the development of a suspension system for the IVGVT. A crucial part of a ground vibration test of a launch vehicle is the boundary conditions. Ideally, you'd want to have it floating in free space like it would be flying. You can't really do that on the ground, so we really have a big challenge in trying to come up with a suspension system to support a launch vehicle. In the case of the Ares 1, it was about a 2 million pound vehicle. That's been done a variety of ways, but our first thought was that we would use what was used previously on the Saturn V dynamic test and the shuttle mated vertical ground vibration test that were both conducted in the dynamic test stand. So our first thoughts were to reuse what they did, and what they had were hydrodynamic supports. And it's a very unique concept that was thought of during the Saturn V test program and was used successfully on 2 previous programs. So we thought the best thing was probably to do what they'd had success with before. We didn't really know the condition of those units. They had been abandoned in the test facility since the shuttle test in the late 1970s. So we had a risk there that they may not be usable. So we had to come up with some alternatives, some backup plans. We had to come up with a plan to get them out of the stand, the hydrodynamic supports, that's the HDS units, and see if they were even viable. At the same time, we had to be looking at alternatives if they were not. So the risk that we're talking about today is how do we select the right suspension system, and if we can't use what we used before, what are our alternatives? The suspension system is a critical component, maybe the single most critical component for the success of the test. You've got to have the right boundary conditions to get the right test data. So this suspension system is highly critical for test success. If the HDS units were not viable, which is the hydrodynamic supports that were used for shuttle and Saturn V, if those were not viable, we would have had to come up with another system. And as I mentioned, we did have some alternatives in our back pockets. Fortunately, we didn't have to use those. But if we could not get a viable suspension system, we wouldn't have been able to acquire the data that was needed. So there was a very high consequence if we did not get this task successfully completed.
The HDS units, to say the least, showed the environmental stresses of being out in the test stand for so long. And I was skeptical of whether or not they would ever be able to be used again. They had been in the weather. I think they were somewhat covered in Building 4550. You could see where there was evidence of water had flowed through the top of the HDS into the bottom of the HDS or the cylinder section. A lot of surface rust, some pitting, a lot of rust around the top of the cylinders. It turns out that ladybugs and wasps really liked the taste of the residual hydraulic oil that was there, and there was a thick layer of that sort of thing and dust in the top of the HDSs. But once they were disassembled and clean, I was surprised at what good shape that, at least visually, that the metal looked. The HDSs are powered by flowing hydraulic oil into these units at a very precisely controlled flow rate and a very precisely controlled temperature. The flow rate will determine how stable the test article will be when you do suspend the test article. The oil viscosity changes the dynamic characteristics of the HDS if the oil temperature is not very precisely controlled. The HDS is really just a simple annular orifice with a varying gap length, and you have to maintain the viscosity of the oil through that gap length, and if you don't, it will change the characteristics of the HDS.
There were a number of mitigation steps to try to reduce the risk of this suspension system. The first one really was to get the hydrodynamic supports, the HDS units, out of the test stand, and those were the units that the Space Shuttle test used. We had to get those out. We had to disassemble them, clean them, do non-destructive evaluation on them, take a look at them and see if it looked like they were still in a condition that they could be used. So that was a critical step. At the same time, we started a parallel activity where we investigated some alternatives, and the primary alternative we thought about was a pneumatic system. And that prototype, that concept was developed by someone in our branch, in the Structural Dynamics Test Branch. And he actually built a prototype, and we did some early testing of that. So we're trying to keep our options open in case the HDS units were not viable. So that was another key step, is to have alternatives. The next thing was probably to do some leak testing of the pistons. The HDS units, the hydrodynamic support units, are a piston and a cylinder arrangement. And inside the piston, there's actually a domed float at the base of it. And inside the piston is a gaseous nitrogen chamber. And so it was critical that we could put that float into position and pressurize that piston and make sure that it would hold the pressure. So that was a key step also, is the leak testing. Now, along with that comes a lot of safety issues. So you have to do hazards assessments and analysis and go through the approval processes with the Safety and Mission Assurance Office. So that was part of it as well. Once we did make the decision that the HDS units were still viable, we went into a functional test program with those units. We reassembled them, we upgraded instrumentation, and we took them into the first phase of a test program. And we had planned 2 phases, only the first phase was completed. In that first phase of testing, we put about 50,000 pounds of dead weight on top of the pistons, and we tested them one at a time. And we both operationally tested them and dynamically characterized them to see how well they would work in the Ares 1 ground vibration test. Ideally, the frequency of your suspension system would be about 10 times lower than the fundamental frequency of your vehicle. So we had to see if these still operated in the range, the frequency range that they did before, and that was just below 1 hertz, about 0.6 hertz. So our functional testing has been a key part. Another mitigation step has been to develop a hydraulic power unit to operate the HDS units. So it was a major effort. We opted not to use any of the equipment that was used before, just due to the age and due to the fact that there's, it's 30-year-old technology. So we had an engineer that designed a whole new hydraulic power unit, and we sent that out for a procurement for the fabrication of that unit. So that was another key mitigation step, is getting a hydraulic power unit in that would actually operate the HDSs one at a time. And we did plan a second phase of the test that would have put a lot higher load on top of the piston, but we didn't ever reach that point.
Part of the function that I had and part of the task I had to accomplish the evaluation of these units was to, number one, do a complete review of the documentation package, which included the original design, concept, and specifications from Martin Marietta, design blue lines, and also a lot of documentation that was used for the testing for both the Saturn V and the shuttle ground vibration testing. Number two, what I had to do was to actually evaluate the material qualities within the HDSs themselves. As a part of that, we disassembled the units into four components. The four components were the cylinder, piston, float ring, and float. The piston just happens to be a hollow piston with threads inside that a semispherical float actually goes into the side of the hollow piston. Float ring screws in, and then the float is able to slide down and rest against the float ring. So we did a complete cleaning and initial inspection. We contracted a company to come in and do magnetic particle and ultrasonic metal inspections to ensure the structural integrity of the units. At that time, we determined that the units were in fairly good shape. We continued with a pressurization test of the pistons. One of the characteristics of these HDS units is that the piston has to be pre-pressurized before it's used to suspend a test article. And we did some high-pressure leak testing on the units to verify the integrity of the piston themselves and the fact that the leak rate would be acceptable. So at that time, we did determine that these components were adequate to use as a part of a suspension system for some future test. At that point in time, we reassembled the HDSs and prepared to go into the next phase of testing. We had to bring some more engineers and more engineering support on board because it appeared that the magnitude of this effort was going to get huge. We were very fortunate to be able to hire two very good engineers, one hydraulic system engineer and an instrumentation and control engineer, that we used and we designed a new hydraulic system to supply the lubricating oil to the HDSs, and also the instrumentation that would allow us to monitor how the HDS was running and to be able to control that HDS.
Top 3 lessons learned. My first lesson learned is to make sure you select the right people for your key tasks. We had a very strong, very skilled lead, Jerry Oakley, on this HDS refurbishment task, and the HDS is the hydrodynamic supports. It took us a while to find out the support contractors that he needed with the right skills, because this is such a unique task. So it took a while, but it was worth waiting on the right skills and the right personalities to work with this team. So the top lesson learned I have is to make sure you put the right people with the right skills and the right personality in a job, because if they don't have even if they've got the right skills and they don't have the right personality, it really can be a detriment. So that's one of the lessons I learned. Another lesson I learned is to always keep in the back of your mind the contingencies and always have alternatives, because you never know when damage might occur to one of the units or some of the equipment, and you'll have to go another route. So always keep in mind the things that can go wrong and be prepared to have a backup plan. The third one is to protect these assets for future programs. As I mentioned earlier, after the Space Shuttle program, the hydrodynamic supports were abandoned in the test stand, and they've basically been subjected to the elements for nearly 30 years before we started refurbishment activities. So if at all possible, to preserve both the hardware and the documentations for potential future users. Another key step that we did when we first started the hydrodynamic support refurbishment activity was to go gather a lot of historical data. There was a variety of NASA archives where we got information. There was actually still some hard copy data that was stored in the test area, and we also had the great advantage that we could consult with two key people that were involved in the HDS activities previously, and one of those is George Van Pregenow, and he actually was the one that conceived of the idea for the Saturn I dynamic tests. And the second gentleman that we were able to consult with was Gordon Scholes. He was a Martin Marietta employee, and he was very critical in the refurbishment activities for the HDS units between the Saturn V test and the shuttle test. So that was a great thing for us to be able to draw on those resources, as well as to have all the documentation available that we were able to find.
As far as the things that we do differently, this job this task, I don't feel like we really missed much where we would just stop and say, oh, I wish I would have done this different. I guess just a combination of having someone like me available that's been through this several times and spent a lot of time on large test stands, knowing what's coming later on if you do make it back to the large test stand to run a big test has been a big help to me, just the experiences that we did have. And the fact that we were able to get such good people to come on board with us, which basically that was 3 engineers, and we've got some real good technicians that help us in the building too. So that's, I can't really nail anything down as far as anything we would have done different. I would encourage people to close their program out in the correct manner. I do know that the state of the HDS, the condition they were in when I received them, was a direct result of probably not having the funding available to properly close the stand out and that program out after they did the shuttle ground vibration test. I think the HDSs would have been in much better condition, although they're reusable, and we've proven that they are reusable. But it's always good to close something out and to keep money available to close it out properly. Other than that, I think just to give the younger troops some advice about the testing. When I first came to work out here, the building we walked in, we had a sign over the top door that said that one good test is worth 1,000 expert opinions, and I've learned that's very true. Test that hardware the way you're going to fly it, and also test that ground support hardware the way you're going to use it.
Do the homework up first. There was a significant amount of information within the documentation generated by the Saturn ground vibration team and the shuttle GVT team. So in diving into the literature first and learning all of the ins and outs of this system and the stumbling blocks for which these past teams encountered and their steps for correcting those situations, we saved a significant amount of time by not having to reinvent those wheels. And so it was excellent. The teams in the past did an excellent job documenting what was done and the difficulties that they had, and they provided us a path, almost a clean path, to go from concept to a system for which we could get up and running and start testing with.